We're going to talk about automated debugging of bad deploys. So the problem I think we've all faced before, I know I have too many times that I care to admit, is you're doing a deploy, maybe somebody else is doing a deploy, somehow there's bad code in the deploy, unfortunately it happens, we're all human, and the success rate drops. So whatever your success rate is, whatever your metric is, it starts dropping way down. In this case, this is actually from a recent issue we had, went down to 20%. Oh God, what just happened? What do we do? Who wrote the bad code? Where is it? So this always is tedious for me especially. I don't know about you, but I always find this really frustrating. There's many commits in a single deploy, and there's many deploys per day. So that means this happens many, many times a day potentially. And you do it once, it takes 5 minutes, you fix the issue, everything's fine. But you do it 3 or 4 times a day, all of a sudden, you're burning out your whole day, and now you're burnt out, and it's a horrible day for you. So let's see what we could automate and sort of make this not as bad for everybody. So the basic resolution, as I'm sure you guys all do, is when something goes wrong, there's a bad deploy, you roll back the deploy, debug it, and that's what we're going to talk about here today. You find the error, you find out what commit caused the error. Often you fix a problem. Usually that's a revert. Maybe you roll forward, whatever it is. Restart deploy and move on with your day. So in this case, there's many kinds of errors, but we're going to talk about a specific type here. There's many kinds of errors you can see in a bad deploy. Maybe a performance regression. Your API slows down. Maybe some important API takes 4 seconds now instead of 100 milliseconds, and everything's really horrible. Maybe you broke a web page. Now the page isn't rendering properly. Get a bunch of JavaScript errors. Or you have empty results. You search for something. You have lots of cute animals. You search for a cute puppy, and no puppies come up. You get a lot of angry users. Or you get a whole bunch of 404 or 500 errors. There's many other kinds, but in this case, we're going to focus on stack traces. Many of the previous errors we talked about also involve stack traces. 500 errors are almost always stack traces. 404s, empty results, could also be stack traces as well. What makes them really nice is they're really, really common. I'm sure all your logs have way too many stack traces in them already. But they also have a lot of information in them, a lot of information we could use to sort of automate the debugging process. If you see a performance regression, oftentimes to figure out what happened, you have to go through and run all kinds of tests and figure out exactly what broke, and it could potentially take a bunch of time if you didn't catch it before the deploy. But stack traces have a lot more information. You can see what parts of code are broken, and you can actually do a lot with that. So the basic steps to debugging a bad deploy are pretty straightforward. You need to find the new stack trace. In this case, we're looking for stack traces. So what happened? There's some challenges here. First, you have to actually find the stack traces on your system. You probably have hundreds, if not thousands, of servers, and logging into all the servers isn't really a valid option here. And once you actually can find the stack traces, you have to find the new stack traces. Maybe your system has many, many, many existing stack traces. And you see your logs, you look at all the stack traces, and you have thousands of different ones. What do you do? And furthermore, we actually have to, when we're looking for an automated system here, we have to deduplicate similar stack traces, and I'll mention that in a second. The second part is trying to find the bad commit. You found the stack trace that caused the system to fail. Everything's been rolled back, but now you want to figure out what happened, who did it, what commit, what could we roll back. So the input here is we have 2 pieces of information now that we know. We know the commits that were deployed based on the deploy system, and we also have the stack trace that brought down the system. So the idea is you pass these into some sort of system in a black box, and the output ideally is we want to find the commit 101 broke the system. That way we could revert it, page the author of the commit, and move on. So talking about finding new stack traces. So the first problem we have is actually finding the stack traces in our system. Many systems now are multi-computer. We can't just log into machines, SSH, look around. At Pinterest, we actually collect all our logs via Kafka and the Elk stack, in this case Elasticsearch, Logstash, and Kibana. In our system, we prioritize real-time results versus completeness. What this means in reality is if you have a big incident, maybe a bunch more logs are being generated, you're generating 1,000 times more logs than usual for some reason, we'll drop some of the logs so we could actually have real-time results instead of delayed results that are complete. When debugging something, if you have no data at all, it's way worse than saying you have sampled results and maybe 1 out of every 100 logs are being collected. And this makes it really, really easy to search for a known stack trace. Here is a fake stack trace, but a real result here. You can actually see if you have the stack trace, you want to look up when did it start, how often is it occurring. It's super easy to do in the Elk stack with a Kibana interface. But this isn't really that useful in many cases. In many cases, you actually don't know the error that you're trying to look for. If it's a new issue, you saw some metric drop, but you don't actually know what the stack trace is yet. You can't just look at the logs. This is an example of one of our dashboards. This is errors, stack traces per second based on some, I think, on file type. And you can actually see we have way too many types of errors to actually look at and say, aha, that's a new error. There's so many ways a little subtle new thing could get hidden in there in all the noise. We actually have to distinguish between new and old stack traces. So to do this, we actually use the REST API for Elasticsearch. I don't know how many people here have used it, but it's really, really, really powerful REST API to do all kinds of really great things for, and it's much easier to do something automated than using the web UI. So to solve this, we actually decided, we say, let's look at two different systems. We say maybe we're doing a canary deploy first, maybe see if canary is working. We'll compare all the stack traces on canary in production. Then after the deploy, we'll say, hey, maybe something got past the canary. Canary is maybe 1% of the fleet, but maybe the error only occurs when you have the whole fleet being after the whole entire deploy is done. So we just look at before and after the deploy, say maybe take a look at now versus a couple hours before the deploy and see if there's any new stack traces that we didn't see before. This way we actually could sort of ignore all the noise, and you don't have to use any strange heuristics to say that error was there for 3 years, we could ignore it. You could have really easily tease out what's new and what's old from this. So once we have all this information, we have potentially, we could actually see new and old stack traces. How do we actually sort of group stack traces together to make it useful? One of the problems you have that we hit right away is you can't just say, look at the stack traces before and after and do a simple string matching, because the deploy could change the line numbers of code. There's some stack trace that already existed. Somebody adds a new line to the top of the file. All of a sudden, all the line numbers for that file are off by 1. Now your stack traces aren't the same. The other problem we all see often is we have potentially optional code paths. So maybe one error that's causing some problem will actually go through 2 or 3 different possible code paths based on some sort of random sampling of something, maybe some sort of stats metrics collection. So to solve this, we actually use Elasticsearch's powerful API to do a filter and aggregation query. So we're filtering by logs containing stack traces on a set of hosts X during some time window, maybe right now the past 30 minutes. I'm going to be on canary versus production. And that's pretty straightforward, but the hard part here is we can't just say look at the logs and aggregate by the actual string of the stack trace, because then we'll actually get thrown off by all the different line number changes and optional code paths. So instead of this, we actually aggregate by a few different things. We first look at exception name. Then we look at, say, we sort by exception name. Then for a given exception name, we look for the file name. And then from there, we look at the exception value. So the example here of some wonderful bad code I wrote the other day. The example here is we have a stack trace, which is a type error. The file name is test.py. And the exception value is unsupported operand. So this is sort of a bit of a heuristic that we decided to use to actually group stack traces together. And it works pretty well in part because the assumption here is that there's not going to be too many stack traces in any given file. So the hope is that it'll be, if you look at the pair of the exception name and the file name, that'll actually be a unique enough pair. One of the problems we actually see for this is the exception value often contains strings. I don't know about you, but our logs often say unable to connect to host X, where X is some IP address. And then if you try to look by aggregate by exception value, you'll have way too many unique exceptions. So we have to use a bit of heuristics there, unfortunately, to tease that out. In our case, we say if there's too many different exception values for a given file name and exception name pair, then it's probably a variable in the exception value. So once we have all this, we actually have to find the bad commit. So the problem we're trying to answer here is now we have a stack trace. We know what broke. We actually want to say, in this case, which of these 71 commits actually caused the stack trace. And so there's many different ways to sort of solve this problem. I don't know about you, but a lot of people do this by hand right now, and we've done it by hand for a long time. There's a bunch of different ways to solve it. You could look at maybe use git blame, look at different files in the stack trace, maybe look at user manager in this case, or data services. Maybe look at all the files that were changed by the range of commits, and you have to scroll through 71 commits in your screen, or maybe you're doing some grep or something like that. And these are all really great ways to do it, but the problem is it's slow and tedious. One of the problems is as the stack trace gets taller and taller and taller with more and more files involved, it gets harder and harder to do this manually. So this takes a few minutes for us when you did it manually, and the goal here is to see how fast we can make this whole process and ideally automate it. So to solve this, we wrote a tool called Git Stack Trace up on GitHub that's available and open source and patches welcome. And sort of the goals here is to make it as easy as possible to figure out which commit caused a given stack trace. So to do this, there's actually a few different ways a commit could cause a stack trace. The first example is one of the files touched in the commit could actually show up in the stack trace. Maybe you changed something potentially unrelated, not actual line of code, but somehow the file ended up in the stack trace. The second way is an actual line of code. Maybe you wrote bad code in the example. Here we actually have 5 plus none that actually caused the stack trace. That's a pretty clear example. It's another way you could cause a stack trace. And the last way is a commit could have caused a new code path to be run, and the stack trace happens further down the stack and somewhere else. You don't actually see the commit anywhere in the stack trace. In this case, is really hard to debug automatically. There's no information in the stack trace about the commit. There's nothing related to it. The files are different. The code is different. So unfortunately, we can't actually easily automate this step, this example. We actually could automate the first two examples. But when dealing with this, there's actually another trade-off we have to make, which is how many results you return. Do you err on the side of too many results, maybe a bunch of false positives where we say, these 4 commits could have caused the stack trace, and in reality, it's probably only one of them? Or do we say, we're not sure about this, do we return no results? And this is the reason why we have this problem is because there's many ways that a file could touch. The file's touch could show up in the stack trace, but maybe it didn't actually cause the error itself. Maybe it's the first line. Maybe there's a later commit in your system that actually caused the stack trace. So now you have a bit of noise in your results. And even that's true also for the line of code in the commit. Maybe there was 2 different commits that show up in that stack trace, and only one of them actually caused the error. The other one was an unrelated change. And so the idea here is that it's actually much easier to review 5 commits manually than look at all 71 by hand. So the goal here is actually to return a ranked list of all possibly related commits. So instead of saying, we know for sure this commit caused the stack trace, we want to say, hey, take a look at these 4 or 5 commits in this list of 71 or 100 or whatever it is. And then it's much easier for a human to look at 5 commits than look at all of them. So when you put it all together, it looks a bit something like this. You say get stack trace, you pass in the range of commits, you pass in the stack trace via standard in, and you can see, ideally, we see John Doe broke the commit, caused the stack trace here. So how does this actually work? These are a few different metrics to actually do this. One thing we do is you look at, if the first example of the kind of error we can look at is one of the files touched in the commit shows up in the stack trace. In this case, we use git log -- raw. And what this does is it shows you for every commit, it shows you all the files that the commit touched, and it shows you in a nice computer-readable format that you can easily parse out and understand what's going on. You can see if it's a modified file, an added file, a removed file, et cetera. And one of the second problems we have when we're looking at this data is we actually have to map the stack trace's file name notation to the actual Git repos notation. So this example, we have services, .. services. You have to map that to services. And in Java, this is a bit more complicated, com.pinterest. Whatever. You have to map that back to the Git repo. So there's a bunch of mapping you have to do after you use the git log -- raw information. The second thing we look at is you actually want to see if a given file has actually caused, a given line number actually matches the stack trace in the commit. So we actually want to see, hey, maybe there's a stack trace on line 487, and the actual commit, see if any commits actually touch that line. So in this case, we use git log -- patch, which generates a patch file, which once again you could easily parse automatically and say, this commit touched these 4 lines in this file, and that commit had an error on one of those lines. One of the problems with this is this actually breaks pretty easily, unfortunately. Say a latter commit comes in and actually adds a new line at the top of the file. All the line numbers are off by 1. So now your actually git log patch information doesn't actually match the stack trace, even though that commit caused the issue. And to deal with this, we use the last tool we use is git pickaxe, which who here has used it? One person's used pickaxe? OK, you should tell more people about it. Git pickaxe is a sort of a hidden tool, I think, in git log and git. It's a really powerful one. It allows you to easily look for there's 2 ways it works. You look for substrings, you look for regular expressions, and it looks for commits that have added or removed a given substring or regular expression. What's really nice about this is if you do a git log and you want to search, say, what commit actually added this line, or maybe what commit added this variable, you do git log --S, and you search for that, and it searches all the code. It ignores things like white space. It ignores things like somebody added a line to the top or maybe renamed a file. These all get canceled out, and you don't see those. So all you see is actually really clear who wrote what. This is also, I think, a lot better than using something like git blame. If you're looking at an old piece of code, git blame may say the last person who actually modified that line. Maybe they added a few white spaces or something, or they added a comment at the end, but didn't actually add that variable you're looking for. And so git log -S will actually tell you that. So we use this to actually look for who added the line of code in the stack trace. Take every line of the stack trace and say, hey, did any of the commits in this range actually add or remove this line? So putting that all together, once again, we have the stack trace over here. So the input, once again, is actually the range. So this is a git range, 8.1 to B3. We're passing in the stack trace. In this case, is stored in a file passed in via standard in, but there's also a Python API to do this as well. And on the bottom here, we actually have one result. We see the results here. There's a few important pieces of information we can see right away. The first thing we see is we see the commit. So right away, we know exactly what commit did it. We see the commit date. And the important thing here, this is not the author date. Git stores 2 different dates in the system. The author date is when the author actually last wrote the commit. And the commit date is actually when it got merged last. So if you're writing a piece of code and getting merged from some development branch onto the master branch, the commit date is actually the important one usually, because that says, hey, that commit was merged today versus that commit was written last week and merged today. And you don't care about when it was written. You often care about only when it was actually committed. We see the author. We also see the subject. Oftentimes, when you're looking for a stack trace, there's some information there, but not all of it's, you can't really figure out, hey, did this commit cause it or not? But oftentimes, the commit message makes it really clear of what happened. So in this case, this is a fake commit, obviously, but be a bad commit or something, modify this system or remove this thing, and it's really clear right away that, hey, that stack trace was caused by this commit if you have a few different ones in the list. In our case, we actually have a system of internal links for our code review, and that's what the link is here. And then the important parts we see at the bottom here, there's two types of signals we're getting at the bottom. We're seeing files modified and lines added. So there's the same file is listed twice under files modified, and that's because the first time we're actually matching data services, we're not matching the line number, and the second time we're actually matching this line 8975. So that was that second example here, git log -- patch is actually telling us, hey, 8975 actually matched. The last thing we see on the bottom here is two different lines actually match the commit and the stack trace. So we see the green and the blue lines actually match directly in. So with this information, it makes it really, really clear, really easily that, hey, there's a pretty strong signal here. There's a lot of matches to the stack trace. This commit probably caused the issue. Now we can actually resolve it quicker. And the way we used to previously do this is you look at the stack trace, you sort of guess, maybe the problem is a data services change, maybe it's a commit somewhere in user manager at the top of the stack trace. You have to sort of guess and look around at a few different files until you found something. It takes a few minutes. Look at 70 commits and try to guess which one it was. Now we actually have 1 or 2 or 3 commits we actually look at, quickly scan, see why they were referenced there, and pick the one that is most likely to cause the issue. So putting this all together, how we use it at Pinterest. So we use this combination of the Elasticsearch queries and git stack trace at Pinterest. We use it every day, all the time. We use it run on every API and web deploy, our front-end systems. And this is one of the nice things I think we didn't realize right away was this has allowed us to quickly detect new rare errors. If you have a really common error, maybe your SLA is dropping, some important metric is dropping down, from 100% to 95%, or maybe down to 20%. But every so often you have an issue that causes, it happens maybe once every minute or so across a large fleet, so it's pretty rare, and you can't look at it in the log system. You can't sort of guess it's there. Your metric is pretty high, your SLA is really high, but maybe it's actually causing the same error for a certain query or something, for the same user seeing the error repeatedly. By using these Elasticsearch queries and actually looking at old versus new commits, stack traces, we're able to really quickly spot really rare issues that we've never noticed before. And the last thing this has really helped for us is a significantly reduced debugging time. Previously, when we do a deploy, we find something went wrong, there's a new issue, we find the stack trace one way or another, but now we have to play the game of who caused this, what did it, and you have to sort of guess and say, there's 80 commits in this deploy, which one caused that, what's going on here, and you have to dig around and sort of hope for the best. And now we actually have a quick list to say, hey, these few commits probably caused it, and you could quickly look it up and quickly confirm with the author, say, hey, did you do this, does this look right, and go from there. And it's reduced the time it takes to solve these problems and deal with them significantly, down from several minutes down to a couple seconds. And that's it. I think I have some time for questions. Thank you.
The microphone in the center of the room, so if you could ask the questions there, don't be shy. I'm sure you'll answer anything you have.
Hey, quick question about the Elasticsearch component of this. Are your searches and your API calls built into Git stack trace, or is it separated? I'm not sure I was understanding.
Yeah, that's a great question. So they're separate. The reason they're separate is sort of two separate parts of the problem. Our Elasticsearch queries are pretty specialized to our use case. There's a lot of Pinterest-specific business logic in there. The names of our systems, our API system name and our Canary system name and our web system name. So that's not really sort of something I thought we could sort of abstract out. The Git stack trace API there's two parts. There's a Python API, but there's also the command line API. And this is really all there is to it. You pass in a range of commits, and you pass in the stack trace and standard in a file or some other way, and it'll output a look at. You run this in the repo you're on, and it'll look through and call a bunch of Git commands internally and output to standard out.
Sure. Okay. Thanks. Makes sense.
So
Yeah.
Yeah, I was just wondering if you could comment again on, do you have any metrics on what percentage of incidents or errors has this actually helped you pinpoint what the culprit was?
Yeah, I don't have any hard numbers, but it's paid for itself, I think, is the short answer. We see it multiple times in a deploy. Maybe we deployed a canary and we start seeing a bunch of errors. It's made that much easier to deal with. We used this twice this weekend, actually, so that saved a lot of time over the weekend. It definitely doesn't catch every case, and there's many cases that slip by this. But it definitely catches a large number of them. It catches a lot of cases that would have been either the Elasticsearch queries catch a lot of cases that are really hard to catch before, and Git stack trace makes it really easy to catch most of the cases and what caused them. It turns out most of the stack traces we've seen are pretty obvious. There are sort of the first two camps of things where there's the commit directly affected the stack trace, and those make it really easy to debug. The latter ones, or maybe a performance regression, are usually hard to debug, and they're a bit less frequent. They definitely take a lot more time.
Could you talk more about the workflow that occurs after you find one of the stack traces that you know you need to remediate? Like, does that go directly to a developer in question, or is there a team that kind of works through that process, or is it automatically?
Yeah, so it's right now it's sort of a manual process. Generally what happens is when you're doing the deploy, something goes wrong, you catch the issue, or after the deploy is done, you find out, hey, there's a new stack trace, there's a commit that's probably related to it. The first thing you do is you ask the author, and if the author is unavailable, you ask any reviewer on the commit. If you're reviewing a piece of code, you should be able to vouch for it, at the very least, or at least know who to talk to next. Different kinds of errors also have different sort of remediation tasks. If it's causing a bunch of 500 errors, and the stack trace is causing the 500s on, say, your home page, that's pretty important. But if it's causing an issue on, say, maybe something less important where the user doesn't actually care about the result, maybe it's not a 500 error, maybe it's just some asynchronous optional logging system is actually not getting called, maybe you just sort of say, OK, we'll fix it in the next deploy. So it really depends case by case. Great, thank you.